Okay. And what do I mean by electrodynamics?
Moving through, so there's a time dependency on.
Okay, so watch.
Time is not zero.
Electrostatics, it's just, there's no time dependence.
So let's do this. Divergence of E equals rho free over epsilon naught.
Can you say that the sources are moving?
Sources move over time, yeah.
Yeah.
Okay, I'm going to put it in, I think, a little bit better context. I think you guys all have it. I'm going to give you my term and then combine what I say with what you guys say. Okay? So curl E is mu0 J free plus I don't know, epsilon partial of E with respect to T. Okay, so if we have what's called electrostatics, right? Electrostatics is the divergence of E equals rho free over epsilon naught, but then the curl of E equals 0.
Right.
So that's electrostatics. And if that's the case, in electrostatics, so electrostatics, then we can say that the curl of E equals 0. Yeah, I know some of that's on. Oh, that's a good one. Nice.
Yeah, that one just goes down.
Okay. All right, the curl of E equals 0. And then we can use our tools. And so these are our vector tools. And what do we have? We have the curl of what?
The curl of the del dot V. How do you
So say it in words too.
The
You
curl of
just said curl of del dot V. What is del dot V? Seriously.
divergence. The
Is it
curl of
divergence?
divergence of
Okay, so
del
is the
grad.
curl. Okay, so I just want you to be careful with what you say, okay? And this is a good lesson. Del dot V is a divergence. It's a vector multiplication. It's a dot product. What do you get out of that dot product?
a
A
scale.
scalar. Does it make any sense at all to take a curl of a scalar?
No.
So what did you say? What you said, was it right?
No.
No.
No
Okay.
way.
Okay, good, right? So what do we really want to say here?
You want the
Curl of gradient.
Curl of a
The
gradient.
curl of
The
the
gradient of a scalar gives you a vector, and you can very definitely take that. Okay, so then curl of, you know, a V. Okay? And so what's the other tool we have?
divergence of the
curl.
divergence of the curl of the vector.
Okay, of a curl, yes, of
Yeah.
a curl. Okay, equals 0. These are, we can prove those, okay? Those are proven like vector calculus identities. So in electrostatics, we have this in particular, so what can we say about E? Using our
That
You
tools,
can write it as the curl of
a scalar.
yeah.
So therefore, we can equate E, what we say equals minus the curl of a scalar V. And then we can plug that into here, okay? Then we have the divergence of minus the gradient of V equals rho free over epsilon naught. All right, and this is the divergence of a gradient, so that's the Laplacian
Laplacian.
of V
That's the Poisson's equation, right?
equals rho free over epsilon naught. All right, and we have a minus in there.
The minus.
But in any case, this is the Poisson equation,
Right.
and when rho free is 0, you get
Laplace.
Laplace's
Laplace,
equation. Okay, so that's electrostatics. All right, we have another field which is called magnetostatics. All right, and magnetostatics is
Steady
is
constant
the
current.
divergence of B equals 0. Right, and we have the curl of B equal mu0 J free. Okay, what does this allow us to do?
Say that B is actually the curl of another vector.
This becomes a curl of the curl of A equals mu0 J free. All right, and then what can you do with the curl of a vector? What vector thing can you use? the back hat rule. And what you eventually get, so this is Poisson, this is Laplace. What you eventually get is you get the law of Biot-Savart. All right? And so this is in earlier chapters. Right? Okay. So that was static cases, all right? But guys, we also spent a lot of time in chapter 9, for example, on what type of solutions?
Plane waves.
Plane waves. Plane waves are solution to what?
Maxwell's equation.
Maxwell's equations, where?
Free space.
Free space. Are they electrodynamic solutions?
No.
Yes,
Yeah.
Yeah, they're transverse.
because time does change with them, so
Okay.
they are dynamic.
Okay, so let's look at this. Let's let this equal 0, and let's let this equal 0. And when we do that, with the zeros in there, with rho free equals 0, and J free equals 0, we essentially have the vacuum solution. Okay, right? The solution, is it electrodynamics? Are there dynamic things going on still?
Yeah.
Yes, it's an electrodynamic solution.
Where's the other time
Solution, but where? In a vacuum. Okay, and when we know the answers are plane traveling waves. So plane traveling waves, right? The solutions are plane traveling waves. And if we drew a picture, they're E, B, K. So here's E, and then B, and then there's K. There's a self-propagating plane waves. All right? So, what are we doing? So everybody all set? We did magnetostatics forever from Maxwell's equations. We did electrodynamics, but we did electrodynamics in a vacuum. What are we doing now?
Electrodynamics in
Conductors.
Okay.
Inside of that electric.
Yeah, no, I mean, we kind of did electrodynamics inside the dielectric in 9, right? The free traveling waves, right?
the wave guides.
What we're doing here is we're finally doing the unabridged solutions to Maxwell's equations with sources, where the sources are rho free.
And that we're used to our other solutions, I hope.
Okay, so now we're finally, so this is the big point that I wanted to get across today. We are finally truly solving, right? This is our first shot at truly solving Maxwell's equations, right? As is. So finally, truly solving Max's equation. Dynamics with sources. And what I mean by sources in this case, J free and rho free not equal to 0. See the big difference where we're going here? Isn't that kind of cool? So basically what we're doing is asking the type of question, if I had a point charge, can you guys figure out the electric field of point charge if I'm holding it here? In the magnetic field? That's electromagnetostatics, right?
Right.
Have you ever been able to answer the question, if I take a point charge and move it, what the electric and magnetic field is from a moving charge?
The magnetic field, but
Well, you know how to calculate the magnetic field from Biot-Savart if you have a current?
Lorentz force.
But
All right,
a charged particle.
But if I just have a charged particle going like this, right? Have you ever been able to fully figure that out? And the answer is you haven't. And that's where we're going right now. All right? So this is what we're shooting for. We're finally shooting for, the real solutions, the full solution to Maxwell's equations. All right? And what we did is we continued to use these tools for tricks. All right? And so, the first trick is, you know, we have, the first, let me write it, so I'll guess I'll write down Maxwell equations again. Divergence of B equals 0, curl of B minus partial B with respect to T, and then curl of B equals mu0, J free, plus mu0, epsilon naught, partial of E with respect to T. Okay. So this is truly what we're trying to solve. We're not making any static or vacuum approximations. Isn't this kind of cool? And this is where you get like radiation from, like where you get the radiation terms and everything, like how, you know, for example, if I'm holding a point charge, you guys know this, right? If I'm holding a point charge, I have an electric field, right? But do I have radiation?
No, let's just jiggle it.
Okay, I've got to jiggle it. So where does that jiggling, how does that produce radiation? And we don't have an answer for that yet. Okay, and that's what comes out of this.
So we can't build microwaves or magnetrons or.
Well, yet. We'll say all these things with a big yet on there, all right? Okay, so what we've done and what we did on Monday was kind of do some gymnastics, and we want to come up with a strategy, all right? And we're going to use the same tools that we used before in magnetostatics for this. Okay, so the first thing that we did is we recognized that even in this true electrodynamics case with sources, the divergence of B is still 0.
Right.
Right, so that allowed us to still say that B could be equal to a,
Curl.
so B equals a curl of A. Okay? Now, if you plug that into this thing, you've got the curl of E equals minus the partial with respect to T of the curl of A. All right? And so you can do a little bit of gymnastic algebra here. It's going to be the curl of E minus the partial with respect to T of A, right? And that's got to equal 0.
Plus?
Plus, thank you. Okay. Now, if I have this, what has to be true about this, or what can I say about this?
That has to oppose the initial one.
Well, let's use a trick.
Yeah, that's the divergence.
Okay, let's use one of our tools.
So the gradient of V is equal to E plus.
So what we can do is we can call this whole vector our potential, our gradient potential. So this could be the gradient, the curl of the gradient of V equals 0.
The book uses a minus sign.
It uses a minus again. Okay. So in other words, we have minus the gradient of V equals E plus the partial of A with respect to T. Or that E equals minus the gradient of V minus the partial of A with respect to T. All right, and what we see is we've got the exact same thing. If we go to the static case,
Right, where there is no time dependence.
there is no time dependence.
So we get minus the gradient of V.
So we recover the static case right away. All right? So our only modification is right like this. But then what we will decide to do is we will try to take this electric field and we'll put it into this equation. This is what we did last time. So we're essentially trying to decouple these. We're trying to do a couple things. We had everything in terms of E and B. Maxwell's equations are in terms of the electric and magnetic fields. All right. We now have the magnetic and the electric fields in terms of a vector potential and a scalar potential. So we're going to get Maxwell's equations in terms of the magnetic and the scalar potentials. And then what we're going to do is kind of what Maxwell did, is kind of combine these equations together to decouple them. All right, and this is what we did on Monday. Okay, remember we kind of came up with this? Okay, and they are equations 10.4 and 10.5 in your book, and I will write them out as follows. So here we go. This is the cleanest way to do everything. So del squared b, or the Laplacian b, plus the partial with respect to t of the divergence of the vector potential has to equal -1 minus rho over epsilon naught. Okay, this is 10.4. And then 10.5 is a little messier. Ready? It's del squared, or Laplacian of a, minus mu naught epsilon naught partial of a with respect to t squared, minus the gradient of divergence of a plus mu naught epsilon naught partial of b with respect to t, and that has to equal minus mu naught j. By the way, I think it's a good exercise for you to say the math as you're writing it down. So it's good exercise for you to keep saying divergence and gradient and curl and things like that, so you know the names. Okay, so the significance is as follows. What we've done is here's what we had to begin with. Our goal was to solve for E and B, right? Now, here's what we're left with. We're left with this, 10.4 and 10.5, where our goal, so here our goal, solve for E and B. Okay, now, what are these equations though, really? These equations are just.
It's just Gauss's law.
The dynamic version.
Okay.
The
Yeah.
dynamic versions of the Maxwell equation.
Well, these are dynamic. These are dynamic Maxwell's
This
equations.
is another way of determining the source of Maxwell.
It's just a different representation of the four Maxwell's equations in terms of the vector and the scalar potentials. But are there anything else than this?
No.
They're this, right? Okay? So all I've got is a new representation. And at the end of the day, here's what I say. Once I do this and solve for the vector potential in B, and then once I do that, if I want B equals what?
Curl of A.
Equals the curl of A. And what does E equal? Oh, sorry.
Negative gradient.
And E equals minus the gradient of B
Minus
minus
partial of A with respect to
partial of A with respect to T. So you got it?
Yep.
Okay. So this is the big kicker at the end of the day. It's a nice board to look at, right?
Yeah.
Yeah, I like that board. Yeah, that's a fun board. At the end of the day, all we're doing is trying to solve for the entire Maxwell's equations that are dynamic with sources, and we applied a couple tricks and got it to look like this. So no big mystery? Okay. So the next step is to solve for B and to solve for A. Alright, it's good to keep this big picture because it will keep you moving through the book very nicely, okay? So the next thing that we want to do is actually solve for, I mean, look, we eventually want to solve for what is the electric and magnetic field of a point charge that's moving, alright? But in order to do that, we got to figure out how to solve for 10.4 and 10.5. All right, and so what we're going to do is we're going to do another trick there. All right, and that's what we're doing today. Okay. And I'm going to follow exactly as Griffiths did in the book. Okay, exactly.
The gauge transformation.
It's gauge transformation. So look, I can leave that big title right there because that's what we're doing. So here we go. We finally have what we're looking for, the true Maxwell's equation, fully dynamic and with sources. All right? So what we're going to do is one of the tricks to solve this is called the gauge transformation. All right? And what we're going to do is we're going to say, geez. You got to say, geez. All right? Or you could say, golly. Wouldn't that be better?
Yeah.
Right? Golly. If, what's that?
And you, it's Latin.
Oh, yeah, okay. If, well, check this out. If the divergence of A were 0, what would you be left with?
Del squared
Poisson's
Poisson's equation. And we've solved that before, right? No big deal. Or, what if you could get this crap to equal 0? What would you be left with? Okay, David, you recognize it. Very close to the Schrodinger's equation, right? Essentially, this looks like a wave equation, right? If this were equal to 0 over here, you would have the spatial Laplacian. Oh, just Laplacian equal mu 0 epsilon naught.
Yeah, just some constant times.
Yeah.
Which is just treat like an operator.
Yeah, okay. So that's our motivation. Look, if we could find such cases where this is true, then maybe we could go somewhere. All right? And so that's the idea of a gauge transformation. And so, you know, what we're going to try to do is we're going to try to mess with this term. All right? And I think this is called the Coulomb gauge.
Yes.
Coulomb's gauge makes this equal to 0. Making that equal to 0, you just were left with Poisson's equation. How nice would that be? All right, and then making this 0 is the Lorentz gauge. All right, and if we could make that equal to 0, then we'd be left with, I like the way Griffiths said this. If this is 0, right, we've got almost the wave equation. So guys, check it out. Here's what he says. If this is 0, we have this, but over this we have 0. He calls that the homogeneous
Yeah, the homogeneous wave equation.
wave
This is the
equation.
non-homogeneous.
And this is the inhomogeneous wave equation. Do you see that?
Which is just 2 more steps to solve.
Okay. But isn't that nice to look at it this way? Okay, so those are the 2 things we're going to do. And the way that we can do that is with a class of tricks which kind of follows what we've been doing, and it's called gauge freedom. All right, and the gauge freedom is, you know, it's a gauge transformation or gauge freedom, and it's 10.1.2 in the book. The way we'll do this is with a trick. And it's called a gauge transformation. Okay. Now here, the basic idea is this. Ultimately, Griffiths talks about a man on the moon. I don't know if you've read this section, but there's really interesting things going on. But he's talking about a man on the moon, worried about the vector and the scale of potential. Because what the man on the moon can't measure those. What the man on the moon measures is the electric and magnetic field. Okay? So ultimately what matters what is measured, or if you want, I don't want to say real, but we'll leave as what is measured is E and B.
Well, I guess that still would mean it's real, and then the stuff that contributes to it is complex.
Well, I don't know about that. Being complex in an imaginary number sense, or
Yeah. I mean, it doesn't change the real measure.
No, it's more like the wave guides
It's observable, I
being
guess.
physical versus the individual waves. Suddenly,
yeah, I agree with you.
let's do more with the wave packets being physical aspect of it.
I like that better. Yeah. It also, quantum mechanics and everything, virtual fields, so it gets a little bit messy, but this is kind of, we're approaching from a purely mathematical standpoint. All right, and here we go. I'm going to follow Griffiths. Okay. Ultimately, what is measured and what matters is E and B. All right, and so that means, in some sense, we don't care what A and V are, as long as B equals the curl of A, right? And E equals minus partial V, right? On minus partial of A with respect to T. So we don't care.
As long as it fills those two equations, it doesn't matter.
Doesn't matter. And so that's called gauge freedom. You're free. So you're free to choose the A and V to be whatever you want. And the strategy is you're going to choose them to make this happen for the Coulomb gauge, or you're going to choose them to make this happen if you're in the Lorentz gauge. All right, so here's how it's going to work. Okay, suppose we let A prime equal A plus alpha vector. All right, and I'll follow it exactly like he said. And let's suppose that B prime equals B plus beta. This is a scalar function, this is a scalar function, a vector, a vector. Right? Okay. Okay, working with this. We want essentially the curl of A prime. So B, let me write it this way, equal the curl of A to equal B, right? That's what we want? Yeah? So I'm doing this extra step, which I think is important to write in.
Saying that the curl of A prime equals the curl of A, so alpha has to be a scalar of some
So
sort.
let's figure it out. Yeah, exactly right. So this is going to be the curl of A plus alpha. That should equal the curl of A. That should equal B.
So the curl of alpha
So
should equal 0.
The curl of A plus the curl of alpha. That should equal the curl of A. That should equal B. So as David said, how could I make that, so to make this true, okay, that and that work, right? But
So
what
that
does
has
that
to be
make
0.
this have to be?
Has to be
Has
0.
to be 0.
That means that has to be 0, so it means the curl of alpha has to equal 0. So that, what does that make alpha?
You could use the tool.
So we can use our tool that the curl of a vector equals 0
So we
for
have to
that
make-
vector equal the gradient of the scalar.
Yeah, so make alpha gradient.
So make alpha, following Griffiths, let alpha equal the gradient of a scalar. Does it matter what scalar function I choose?
Anything. This is
Absolutely anything. Right?
Right.
Why is that okay? Why is absolutely anything okay?
because
Will
the
be true
curl
for
of a
absolutely
gradient
any function.
is 0.
Okay. Because the